Yes, sir. So,
Hello.
hello, sir. Am I audible?
Yeah. Yeah.
Yes, sir. So, sir, we can start the second session.
Okay. All right. So can you just tell me, like, after 15, okay, this is 1 hour 15 minutes, correct?
Yes, sir.
Okay. All right. Sorry for the confusion again. So
Yes, sir. Due to time zone, sir.
yeah. Anyway, I thought it would be easier for you guys in the morning, but anyway. So uh, again, welcome back. I mentioned this in the last slide. So these are the four methods we already explained: that mechanical, hydraulic, chemical, and this modification by inclusions, and all these different methods you mentioned. So others here you mentioned that the removal and replacement and the thermal or electrical. So I'm just going to go mostly now this mechanical modification part. And then also basic compaction method, and then also the dynamic compaction and blast densification. The first thing is I'll cover only the mechanical densification part now. As I mentioned, removal and replacement. So these are the different things people use. Removal as this easy way to remove and replace, but sometimes, as I mentioned, it's not feasible. And in situ ground improvement, we mentioned that there are several other methods: pre-compression, vertical draining, in situ grouting, stabilization reinforcements. Okay, so what is replacement and removal? So these are the things. Is the oldest method to remove. Simply remove the bad soil and replace with the good material. Okay? So you have to be careful sometimes. So when you are using this, is a clay you replace with gravel, but sometimes if the gravel is mixed with clay, its behavior is like a clay, so it's just useless. And that's why people are using geotextiles or geogrid into that, so that it's a separation between these two materials. Okay. And so and then what happened? The soil will have to replace, include contaminated soil and organic soils, or also method is usually practiced only above the groundwater table. So obviously the replacement you can use it when the soil is above the groundwater table, above the groundwater. So if it is a wet soil, you cannot use this method, replacement removal. So you see the original figure in this figure: original strong soil, original soil, and loose soil. So what I need to do basically, soil excavated. So basically, again, the compaction process, correct? Excavated, add some water, and then compact in layers. So that's why is a cell water content adjusted and adjusted in layer. So basically, that's why you call the engineered soil, correct? So engineered soil, real soil, we don't know what type of soil is there. What is the void ratio? What is the porosity and other things? So here we know how much is the density, how much is the water content, everything, and then you know how much it can the soil can load the soil load. It can take the load. Then the partially replaced soils, instead of whole soil, you just layer of material, new material we added, and compact the soil, existing soil. So this is one partially replaced soil. This is the figure D at the corner here, the new soil. So you just put all new material in different and compact it in layer wise. Okay. Then modified with soil additives. So again, you can use different additives and then compact it and then do this. Okay, do this in layers. And then also the reinforcement soil, obviously, you can do this and put reinforcement layer and then compact it and then put another reinforcement layer like this, or using geocell. So this is basically the removal or excavation of the replacement. So excavating the poor soil and replacing with having desired properties is normally economical. So obviously there are every method some advantage and disadvantage. When the soil is, so it can treat it up to 3 meters. So you cannot do more than that. And the water table is below 3 meters, obviously. It should be in dry conditions. So what are the different 4 steps over here? Excavate the soil, modify it, place it with modified soil by replacing a thin layer. So you have to put it in a thin layer. So that's why the compaction, when you do put it in a 3 layer, in standard Proctor, UNIC, or when you use the roller and compactor, so you have to put it in 3 layers. And then also compact each layer with rollers. We'll talk more details. And then 4 process of modifications. First thing is alter the water content. You change the water content. Then the V is basically the replace, solve replace, and then the mix with additives, and then include or reinforce. And as I mentioned, this is removal and replacement is easiest and oldest method. So another method, in addition to the 4 process over here, there is also thermal process. As I mentioned, it can be thermal, it can be freezing. Okay, so thermal process is rarely adopted, expensive and skill involved. So when the suitable you are eating heat, right? So it's suitable for wet and organic soil and heat up to 500 degrees Celsius to remove the organic matter and use modified material. So there, again, this is a different thing, and we'll talk more detail or organic or peat soil in that in thermal process. So some of the method situations in this found in this effective are economical. So again, replacing with poor compaction of excavated soil, adjusting with the moisture content, and then increase the bearing capacity. Replacing with a layer of sand intercepted. So obviously sometimes the clay layers, you put a layer of sand and then put clay again and then put layer of sand. So basically you're putting sand sandwiched between this clay layer, and then when you apply a load, so basically the water can go easily, in that clay layer. So because the sand permeability is higher, so that can basically settle quickly, and that is the soil properties will be better. Replace with the new soil using when good quality of soil is available, very nearby sites. So that is, again, availability of the material. You mentioned the different points. Replacing the soil with cement as an additive is useful when good quality soil is not available. So in that case, you need to use some the cement. Again, people are these days talking about sustainability. Ordinary Portland cements, even the production of it itself, it generates a lot of CO2 and greenhouse gas. But again, when there is no choice, we have to use it. Okay. And then idea is basically increase the strength of the subgrade for the road subbase. And then also replacing the soil with lime, reduce the sinkage and swelling behavior of high plastic clay. Again, what type of soil you're talking about. So we need to use that different type of soil. So and then what type of stabilizer you're using. So again, replacing the soil with bentonite as an additive is useful in constructing impermeable. So suppose if you're using something impermeable barrier, so you can use a landfill liner design. So in that case, we need to use that impermeable layer. So use bentonite or bentonite, mostly bentonite. Replacing with good soil layer of geogrid, useful for the reduced differential settlement at the base or large diameter storage tank or base of the environment. So you can use that also for geogrid. And replacing with excavated soil, thermally treated, useful when it is peaty soil, so it's highly organic and too much of water. So in that case, thermal modification is useful. So then now I'm just going to talk about the mechanical compaction. So mechanical method. So basically how to increase the density of the soil without adding anything, just like normal compaction. So this is basically, already compaction. The compaction is basically expulsion of air from the soil sample. There's a difference between a compaction and consolidation. Consolidation is expulsion of water from the soil sample. This is expulsion of air from the soil sample. So many earth type, any construction such as dam, retaining wall, highway, airport require man-made place soils or engineered soil or field. So when you are constructing from scratch, so we know what density we need. We know how much the load it can take. So everything is predetermined. Okay. So here the compaction is to the compacted soil, that is to replace the dense. So basically what you do, the compaction, so we increase the density of the soil. Okay? Increase the density of the soil. Density of the soil is more, meaning it take more load, and then obviously the shear strength is going to increase, the settlement will be less. So densest is achieved through reduction of air voids in the soil. So that is the definition of consolidation, with little or no reduction in the air content. Okay. So what do you need to do in consolidation? Again, already, I'm just telling it again. So it's very fundamental things. What happened, for when you do compaction test, So compact the soil, meaning if we add water and density is increased, add a little bit more water, density is increased. So, and then it will reach a maximum value, that is the optimum moisture content or water content, that density will be the maximum. And then if we add more water, obviously the density is going to decrease. Okay? So the standard Proctor graph, so basically what you need to know, so what is happening basically in consolidation. So soil particles, we add water, so all the water is coating with that the soil particles. Okay, and then when you add some mechanical energy, just using hammer, so basically they are sliding each other, and then they adjust themselves, and then making it closer, the density is increased. Okay, so that's why the density is increased. So with after optimum moisture content, what is going to happen? So basically there. Density is increased, so when you add more water, so the water particle is replaced with the soil particle. So obviously the unit weight of water is less than the unit of the soil, so obviously the density is going to decrease. The process, again, this is the difference between this process must not be confused with consolidation, in which the water is squeezed out under the action of continuous static load. So obviously the consolidation is different, so we have the expulsion of water from the soil sample. So that's why, it's Terzaghi's theory of consolidation. So when you do the consolidation test, it's a bit different. So first you saturate the soil sample, and then you get rid of the water, right? So it's a bit funny. You want to get rid of the water, but first you add this water to make it saturated, and then you apply load to get rid of the water. So as I mentioned, the compaction is the shallow compactions. We will know what is the theory of compaction. So again, everyone knows this, but I'm just going to go through again. Properties of the structures of compacted fine-grained soils. So what is going to happen? Again, you need to the fine-grained soil. You need to know there are two types. For the silt and clay, mostly the fine-grained soil. These are the two fine-grained soil, and they are the structures. For the coarse-grained soil, the structures are single-grained or maybe honeycomb. Single-grained, again, it can be like a granular type of soil particles. And then it can be honeycomb for, it can be loose, it can be dense. For clay, it's a platy structures. And when you compact it, mostly, depending on the fabric arrangement. So again, it can be flocculated or dispersed, depending on the compaction state. So most of the time is a dry side of the optimum. It is more flocculated edge to face, more strength. And then when it is wet side of the optimum, so mostly it is the parallel, So that's why we need to know the structures of the compacted fine grain. Field compaction equipments. What are the different field equipments generally used to increase the density of the soil? And then field compaction control. So how you know that the density is achieved at the field? So we need to go to the site and do the in situ test. There are several field tests you need to do, and then And then estimating performance of compacted soil. So now when you compact the soil, so now you need to know the field compaction. So now how much is what is the performance of this compacted soil? So again, general compaction methods. So we have, as I mentioned, the coarse grain and fine grain. So when you talk about coarse grain, as per USCS, we'll talk about gravel and sand. And fine grain, I'm referring silt and clay. Okay. So there are lab tests and field tests. In the laboratory for the coarse grain, granular type of soil, they use the vibratory hammer, So we don't compact it for the sand. So when you compact with the hammer, so that will splash out. So we don't want that. So most of the time, the coarse grain, we use vibration. For fine grain, we use the falling weight or hammer or kneading compactor or static load and press. This is generally used for the laboratory. In the field, the same thing. We have to use the hand-operated vibration plate, motorized rubber vibration plates. We will talk more detail. And then also in field, for the fine grain, we have hand-operated tampers or seafood rollers or rubber tire rollers for the clay type of soil. So then what is the advantage of compaction? Again, idea is repeatedly I'm telling the increase in the strength of the soil, shear strength. Again, the shear strength is the parameters, that tau is equal to C plus sigma tan phi is the cohesion and angle of internal friction of the material. So most of the time, for the coarse grain soil, the shear strength is coming from this friction. How much is the angle of internal friction of the material? More friction means more strength. And then also for the clay type of soil, more stickiness or cohesion. There is an intrinsic cohesion. There are different type of cohesion is there. And then the decrease for future settlement of foundation. So again, if you compact the soil well, then the settlement will be less. Decrease the soil permeability also will be less. The water sometimes ingests to the soils and create problems, so that can be avoided. Stable against the volume change for other factors, wetting, drying, and freezing, thawing. Relative durability, relatively durable and safe against deterioration. Increased slope stability and embankment, and can prevent the buildup of large water pressure that can cause the soil liquefied into the earthquake. Okay? So these are the few things, the advantage of compaction. Lab test, again, we know already there are Proctor tests, standard Proctor tests. So RR Proctor is the one developed during the World War II. And then, so idea is we need to find out how much is the optimum quantity of water you need to add so that you can get the maximum density. Okay, and the impact compaction. So obviously, when you do this impact, so obviously this is called the standard practice impact compaction, and then depends on hammer drop, how many times the hammer. So most of the cases is 25 times. Weight of the hammer, height of drop, number of drops, number of soil layers, and the volume of the mold. So these are the different factors we need to check. So over here, this is the standard Proctor hammers. These are standard things. We have a standard mold is there. There's a we generally compact for standard Proctor compact in 3 layers. We have a standard hammer, 2.5 kg hammer, and 25 number of blows. We put it in 3 layers, and every layers you have to scratch it, and then you have to there are mechanical hammer. There are manual hammer, so you can use. So manual hammer, we rotate it. Mechanical hammer is the mold is rotated, but the hammer is fixed. So we can do what type of test you need, what type of density you need. Accordingly, you can do the standard Proctor test or modified Proctor test. So over here, the standard Proctor, the difference, the mold is same. Hammer is, the weight is different. This is 2.5 kg. This is 4.5 kg. Standard Proctor is 30 centimeter height. This is 45 centimeter. Number of blow is the same. Standard Proctor 3 layer, modified is 5 layer. And then the mold size is same. Obviously, it's more energy over there because you put in 5 layers. And then also here it is. And then weight of the hammer is also more. Okay. So the modified test was developed in the World War II and U.S. Army Corps of Engineers. So basically, to design the compaction required for airfield or support heavy aircraft. So that's the one. Most of the time, when you design something heavy load, so we need to use the modified Proctor, or just for example, airport runway or anything. So, and also people are using this in the kneading compaction method. So again, it's a smaller method, it's a Hubbard miniature compactions. You have a mold, a smaller mold, 2.1 inch height and 1 inch diameter. And then also there is a spring, different types of springs are there. And then you have to press it. And because the height of the teeth is very small, so we need to find out how much is the area. So most of the time we need to do different trial and error to find out depending on what is the stiffness of the spring. So based on that, we can use the modified Proctor test, miniature Proctor test. So idea of using this miniature mostly for the laboratory test, we don't need too much of samples. Suppose if you're using chemicals or if you're using any polymers or others, we don't want to waste too much stabilizer or So here, so idea is only thing is you can put like a 5 layer. Sometimes you have to put 5 number of blows and then 5 layer. That'll be good enough. So depending on what type of spring are you using, you need to, depending on the stiffness, so you need to calibrate. And most of the time, you need to do the same soil, check with standard Proctor and modified Proctor and see both should match. These are the, the two Proctor laboratory tests. One is standard Proctor and modified Proctor. And in the first one, the standard effort. So obviously, if you increase the standard the hammer, so obviously the density is going to increase. and then optimum moisture content, it shifts towards the left, right? So these are the different rammer weight, height of drop. People did some experiment for the ASTM. So again, what is happening over here? So the weight is the same, and then and for the same soil gradation, and then see what is happening over here in the modified and the standard method. Okay. So and then so obviously, as I mentioned, you can easily calculate how much is the energy we're adding. So it depends on how much is the weight of the hammer, how much is the height of drop, number of blows per layer, and the number of layers, and divided by the volume of the mold. So you can easily calculate how much is the energy added. Procedure, again, everyone knows, but I'm just telling. So first thing is, if you're doing manually, so you need to do first 1, 2, 3, and 4, and then gradually go on. Oh, is it good? So then there is the manual procedure, as I mentioned. But if you are using mechanical hammer, so then the hammer is falling at a fixed, at the same place, but the mold is rotating in that case. Okay, and then obviously you need to find out how much is the density, but that density is we are adding water into that, so you need to know how much is the weight of the soil inside the mold. The volume of the mold. You can find out the density. Density is equal to mass by volume. You can easily find out, but it is the weight density. But if you know after the standard Proctor test, you take out the soil sample and you put it in the oven and find out the moisture content. Then you need to find out how much is the dry density. Dry density is the weight density divided by 1 plus moisture content. So easily you can find out the dry density. So so the standard Proctor graph is basically the plot the moisture content versus not the weight density, the dry density. So this is a standard graph we are interested in, like you see the standard Proctor in the bottom graph is standard Proctor, and then the graph B is the modified Proctor, same soil. So modified Proctor, the energy is more, so density is increased, but at the same time, the optimum moisture content is decreased. It moves toward the left. And then we have degree of saturation, obviously 100%, that is 0 error line. So this line should be close to this line, but it should not be beyond this line. There's something wrong in that. So obviously these are the different degree of saturations. So again, you can easily draw this line from there, the unit weight of the soil, gamma D is equal to, you need to know the specific gravity, GS times gamma W divided by 1 plus E. E is the word ratio. Again, E is, you can find out E is equal to GW by SR, that GSW times GS, specific gravity of the soil, times W divided by degree of saturation. From there, if you for degree of saturation, SR, if it is 100, you can use that SR 100 for the particular point, so you will get that graph. If you use SR is equal to 80%, so then you will get that line or different line, and then also the line of optimum. So as I already mentioned, so this is the graph, like what is happening. So in the standard Proctor graph, initially the strength is density is increasing as you more water, and then basically the increase of density due to the compaction, because water will forming the coating of the soil particles, and then they are sliding each other with the hammer effect. So then they are adjusting themselves. But that's why the density is increased with adding more water, and then if you more water, then the soil particle will be replaced by the water, and then also density is decreased because the unit weight of water is less than the unit of the soil. Okay. So this is already mentioned. So basically, we are interested in how much. So it's go on increasing and then decreasing. So we are interested in how much is the maximum density and how much is that at what water content? That is the optimum water content or water content. So we are. So obviously here I just want to tell what is happening in the dry side of the optimum. So dry side of the optimum is basically So here in the weight of this is the optimum moisture content. So what is the behavior of the soil on the left side of this, the dry side, and what is the behavior of the clay on the right side? Okay, or wet side of the optimum. So these are the different properties. Dry side is more random. As I mentioned, the clay is flocculated and more flocculated structures, edge to face, and the wet side is more oriented, like a parallel, more dispersed. Permeability is more permeable over here. Compressibility, more compressible in high pressure zone, more compressible in low pressure range, and the swelling more for high water efficiency, and the shrinkage more. The strength is obviously the dry side is higher, and then wet side is lower. So these are some of the things you can see more details, but from this Holes and Kovac, but I'm not going to go in detail. So most of the time, what you need to do basically for the single compactions, or I'm just going to go over here. So this is, you can see over here, the water density relations with 8 soil compacted standard Proctor. This is using the standard Proctor test. So one is, you see the well-graded sand with, SWSM. Number 2 is the well-graded sand, silt, well-graded silt with silty sand. Third is clay sand, okay, clay sand. And this is low compressible clay. Number 4, sandy lean clay. And then also, this is also low compressible clay. And then also low compressible silt. And this is highly compressible silt or fat clay. And this is poorly graded sand. SP is the poorly graded sand. This is number 8. So from a geotechnical engineer, so you can easily find out what type of soil we have depending on the soil from the standard Proctor graph. Okay. So standard Proctor graph, most of the time, this is more well-graded. Obviously, it depends on the particle size, right? The particle distribution graph, when is all the particle size in a soil, is all the different range of particle size is there. It's much better. We need that type of soil so that the bigger particles there and the smaller particle go into the the voids of the bigger particles, and then we can compact it. The void ratio will be less. You can compact more density. You can achieve more density. So poorly graded soil is not good. So it's a poorly graded means we are just all soils particles are the same or uniform. So that is not good. And then also depending on the soil. So most of the cases for granular type of soil, you add a little bit of water, then the changes is really drastic. For clay, the standard Proctor graph is more flat. You just go increasing because clay can hold a lot of water. It's water. It can so that's why it is go on increasing. It's more flat and then like this. So from this, you have an idea what type of soil is there. Okay, from the standard Proctor test. So these are different properties of how much percentage of sand, silt, and clay, liquid limit, and plasticity index, and so you can easily find out how the shape of the particles, standard Proctor graphs looks like. And also effect of soil type, you need to know the particle size distribution, you need to know the shape of the soil grain, you need to know the specific gravity of the soil, because the density is different. Gravity, gamma D is equal to GS gamma W by 1 plus E. So we need to find out the void ratio, amount of soil, and the clay type, clay mineral present. So these are a few things you need to check. So here again, same soil, but different effort, compaction effort. So first one is anything good? Everything? So laboratory compaction static test, 200 psi, modified Proctor. So everything is like a different effort, how the density is going to change. Okay, so you can find out from here. And so majority of the field compaction is controlled by the dynamic properties of this. So I'm just going to go now for the fine-grained soil. So what is happening in the microstructure level? Fine-grained, as I mentioned, this is mostly the clay type of soil. So you see here the compacted dry density, again, a dry side and wet side of the optimum. So again, you see here, and the wet side is much more dispersed, and the compaction on the left side, you see there is much more flocculated, and the strength is much more on the dry side. So, and then also you can see here how the permeability is going to change, with, if you do, this is a standard Proctor test. If you do the same moisture content, if you do the permeability test and the density, same density, you see the permeability is changing up to that optimum moisture, a little bit more than optimum moisture content. And after that optimum moisture content, the permeability is almost the same. There is no change. Okay. Field compaction, now this is the laboratory compaction. So basically using more compaction effort, then you'll get more density. Okay. So now to simulate the same situation in the field, there are different types of roller or compactor available. So again, this is like a shallow type of shallow compaction. Okay, shallow compaction. So one is smooth wheel roller. The next one is vibratory roller. Again, depending on the soil type, you need to use different type of roller. Then the third one is the pneumatic rubber tire roller, and the fourth one is the ship food rollers. Okay, so the main limitation of these conventional compaction methods, the depth of improvement is limited. Although we use different type of heavy roller compactor, depth is limited. So when you need more depth of improvement of the soil, so then you need to do the dynamic compaction or blasting or any other method. So we'll talk about now what are the different methods available for the field and how much is the load you need to apply, what mechanism, and how much is the depth of improvement for every roller type. Okay. So again, when the depth is improvement limited, it is mainly used for the field, not for in situ natural geomaterial. So when you just, for example, you are constructing a new embankment, so you are using a field material and then compact it in different layers, and then you compact it. Okay. So sometimes, you have to put it in a certain layer. So mostly 30 centimeter, more, if you put more than 30 centimeter, the effect of this hammer, effect of this roller is not going to do that, So that's the, advantage. Then you have to go to the site and do the field test, right? So, I have one experience with this compaction, I used to work for a Dutch company when there was the compaction, most of the time the compaction, people, okay, we did this compaction, in the evening time on whole night. Problem was, they used to do, instead of layer wise, they put a thick layer of clay and then just roll it. It's not going to occur, right? You're not get the exact density whatever you need. So what do you need to do? We need to do the field test and then check whether it is okay or not. Okay. So that is in Paradip. I used to work there, and then we used to do a lot of CPT and other tests. And then also one of the tests is like a field test using different methods. So I'm going to talk about that. So geomaterials should be within the moisture content, close to the optimum moisture content, or more effective. So we need to know from the standard Proctor test, what is the maximum optimum moisture content. You need to use that amount of water so that you can get the maximum density. And it is challenging to achieve uniform compaction geometry in a large area. So again, in the lab is more controlled test, and the field is a bit different. In the huge area, the road or any areas, it is very difficult to check the quality. Okay. So first one is like a smooth wheel roller or drum. So here you see that it covers the whole area, 100% coverage under the drum. Okay. And the contact pressure is 300 kPa. So this is around 7,936 pound per square feet. Can be used for all type of soil except for rocky soils. You cannot use for rocky soils. Compacting effort is the static weight. Because of the heavy static weight is going to compact. Most common use of large smooth roller is for proof rolling subgrade and compacting asphalt pavement. So this is the one. And the most important thing is here, effectively, it is compacts effectively for 20 to 30 centimeter only. Okay, 20 to 30 centimeter, it can compact. So it can, so that's why if you put more than 30 centimeter depth of soil, so it is not very effective. Okay, although it has heavy load, but it is, there's a limitation, because of the static load. So this is smooth wheel roller, drum roller. Then vibrating drum or smooth wheel. So this is smooth wheel again, but it's a vibration takes place. So vertical vibration attached to the smooth wheel drum. And the best explanation why the roller is vibrating, because it's an eccentric load. Arrangement occurs due to the cyclic deformation of the soil produced by the oscillation of the roller. So basically, the two eccentric load placed into that, because of that vibration, it vibrates. And here the load is the static weight. Earlier one, it was only the static weight, right? So it was the static weight over here. You can see static weight. This one we have static plus vibration. So this is suitable for granular soils. So granular soil is always suitable for vibration. So not that the compact, because if you compact it, then it will splash out the soil sample. So then, so this is the vibrativity roller, how it looks like. Inside there is a off-center rotating weight. So because of that, it vibrates. This is a vibrating plate, hand vibrating plates, how it looks like. Then now the question is, for when you're using this roller or compactor, how many times you have to do it? Okay. So obviously, ideally, you have to do the compaction, and then when the compaction is done, you have to do field test, in situ test, using different methods. So most of the cases here in US, we use nuclear gauge. You can use any method, sand replacement, rubber balloon, water replacement method, or any method you can use, or simple core cutter method, you can find out how much is the density. So here in this case, you see the vibratory compaction for the sand, and you see the first graph in A, number of rollers. So it's 1 times. If it is do 5 times, if you do 15 times, you do 45 times. You see. So how the density is increased or decreased. So you see here the density on the in the top scale, the same unit, different unit, pound per feet cube or kilonewton per meter cube. It's not much difference if you see the 5 and if you see 15 or 45. Not much difference. So most of the time is optimum is if you do the same place like 1 time and 5 times is a lot of difference. But if you do 5 times, 15 times is not much different. That is the idea of this figure actually. And it says, you see the 75%, minimum required relative density of 75% is 5 roller passes. So most of the time, again, so we need to do like a 95% of the optimum, right? So 95% of the optimum, so that is the maximum. You will get the better results, depending on the site conditions. So over here, then the pneumatic rubber tire roller. So this is not that the whole area is going to cover, because some portion is, the tire, there is a gap over here, right? So this is not covered 100%. So this is 70-80% coverage. Tires are closely spaced, 4 to 6 in a row. So depending on situation, the different company has different. And then the pressure is 700 kPa, is 14,600 psi pound per square feet. It's much higher contact pressure, can be used for both granular and fine grained soil. So here the compactive effort is static load plus kneading action. So earlier one, normal one, the smooth roller is only the static. The second one, vibratory, static plus vibration. So now this one, pneumatic tire, static plus kneading action. Okay. So it can be used for highway fields or earth dam construction. So anything you can use for this. So this is how it looks like. The Caterpillar, Ingram, a different company has their different arrangement. Then the seafood roller. Seafood rollers, many round or rectangular shape, feet attached to the steel drum. Is covered is again 8 to 12% coverage, and contact pressure is 1,400 to 7,000 kPa. Is very high again. You see the 29,340 to 147 psi pound per square feet. And it is suitable, best suited for clay depth. So if there is a clay, so use this seafood roller. Here, the compacting effect is static weight and the kneading actions. Static weight and the kneading actions. So, and as I mentioned, it's very effective for clay type of soil. Okay. And there's another one is not very common. Is a grid roller, grid or mesh roller, and it is compacted for suitable for weathered rock or well-graded coarse grain soils. Is very, very gravel, or boulder and cobble. Then it is good, and it is basically the weight is between 4.5 tons to 15 ton ballast. You can use for that to compact this. So again, so basically because of this weight itself, the static, and then also a little bit of kneading actions for this case. So this is here in US, most of the time before this any construction site, so people use this type of machine to just excavate a little bit on the top portion, remove there is the grasses, and then just start the soil and then level it and then do the compaction. Okay. I don't know. So this is in our place is very common over here. So now another compaction is the intelligent compaction. So intelligent compaction is a continuous quality control. So normal compaction, what you do the compaction at the site, and then, okay, depending on the contractor. Now the contractor say we are done. So as an engineer, you need to go to the site and do the field test, okay, in situ test, and you check how much the density at the site compared to the lab, and then find out how much is relative compaction, right? So, but here in intelligent compaction, so instrument has itself the automatic measurements, and then the operator can tell with the color code. So there is a sensor in the machine, and then also and also the adjustment and optimization of the vibrating amplitude. You can change the frequency and the speed using a feedback control system in the machine operator to achieve the uniform compaction and desired target level. So the operator can control everything in a computer screen there itself, and then you can check, okay, when you do the compaction, it will turn to green. So when this green means, okay, you are done. So that is already instant quality check. So this is how it looks like. GPS linked to the site, so you need to know what area you are compacting. So that's through the GPS. You can find out an onboard computer screen. So again, you can get this type of what type of frequency, what type of weight you are using. So everything should be there, and there is a color code, so you can find out and change accordingly using this intelligent compactor. So there are different machine drive power, and then also the compaction meter value. So all these things you can easily find out from this. This is I've taken from this Venapusa's paper from Iowa State. So these are different instruments we have here in US available. The Caterpillar, Dynapack, Sakai, so all these instruments. So from there, easily you can find out as the compaction is going on, you can see the color change, and then if it is a green means you are done. So it's very easy for the contractor, the operator, and then obviously you need to go to check the quality control. So people have already did that, so it is much more convenient to use. But again, the thing is you need to have these type of facilities available to the contractor. So I'm not going to go in detail, drum roller, different type of drum roller, and then how that the different type of what they measure basically, So suitability of this intelligent compactions is similar to the conventional compaction roller, can be used to compact the natural subgrade or filling range of cohesive to cohesionless geomaterials. So depending on the soil type, again, you need to choose that different type of roller. So I see intelligent compaction rollers are even more suitable for non-uniform subgrade condition than conventional compaction roller. So advantage of this, again, this is 100% coverage, the compaction properties, like a smooth drum roller, 100% coverage, and not like ship foot or pneumatic tire. Helps the operator to identify which spot for further compaction or treatments, and then also the quality control and quality assessment. So you need to know, the operator will know immediately which portion is weak, so then you compact more again. Avoid over compaction, so no need to do when the compaction is done. So no need to do the over compaction, just save energy and money, and reduce the number of passes. So again, depending on the soil type, right, and the water content. So when the compaction is done, how many passes, as I mentioned, like if you do 1 pass, if you do 5 pass, if you do 5 to 10, it's not much difference. So if it is already 5 pass or 6 pass, it's already turned green. So meaning no need to do it again. Serves as a full coverage of quality control, quality assurance, minimize the need for field inspection. So again, obviously after this compaction, also you need to go to most of the time, you have to go to the field test just to check whether the instrument is giving the correct results or not. But you need to have minimum, and the result is more efficient and uniform compaction. So limitation is the equipment is more expensive than the conventional compaction equipment. It requires managing and analyzing significant amount of data. Obviously, every time with the GPS coordinate, you take the data and then coordinate and find out more you need more data. You need to analyze more data. And then these methods are often required test strips for calibration of the targeted compaction values prior to production compaction. So obviously, you need to check first, for a particular site, you do this compaction and do the test again. So see, whether it is giving correct results. So these are the summary, as I mentioned, the field compaction. So in this figure, you see the 100% clay, 100% sand and rock. So what type of instrument roller? So seafood roller, you see that if it's a clay, 100% clay, seafood roller is more suitable. This is a static load, static weight and kneading actions. If it's a grid, static and kneading actions. If it's a vibratory, static and vibratory. If it's a sandy type soil. If it is a smooth steel drum, it's a static load again. So these are the different types of soil, and then what type of compaction effort, type of compaction, whether it's static, whether it's kneading, whether it is vibration, whether it is impact. So you can easily find out from here. Now the compaction control. So when you've done that compaction, so how you need to check? So obviously we need to do the test. So one test for 1,000 meter cube of compacted soil. And we need to check what is the minimum dry density. We need to check the range of water content. So to find out the field density, there are several methods. Core Carter method, sand replacement method, rubber balloon method, oil replacement method, nuclear gauge method. So nuclear gauge is very common over here in US. So again, everyone knows this, but in sand replacement method, what we need to do, we used make a hole in the ground and then put a jar and then the sand. So most of the time we use the Ottawa sand. We know the specific gravity of the sand. We know the weight of the sand, and then find out. Basically, you take out the soil sample from here in this hole and then fill it with sand to find out. So basically, if you know the weight of the soil, if you want to find the density is equal to weight divided by volume. So the volume is over here is irregular volume, right? So now we need to find out the volume of this irregular hole using this standard Ottawa sand. We know the weight of the Ottawa sand. We know the specific gravity of the Ottawa sand. You know how much the sand gone inside, and you can find out the volume of that. So if you know the volume of that hole, you can find out how much is the weight of the density of the site. So that is the weight density, but again, you can find out the dry density if you know the moisture. Water replacement test, again, same thing. We just fill with water. Okay. Then rubber balloon test. Also, is an instrument over here. You need to pump the balloon, rubber balloon, and the balloon will be, instead of earlier one, you fill it with sand. Now the balloon will be inflated into that hole, and then it will be filled with water. So we can find out how much is the water inside that hole. So we can find out, the specific gravity of the water is 1 gram per centimeter cube or 9.81 kilonewton per meter cube. If you know that, you can find out the volume of this hole. If you know the volume of the hole, you can find out weight divided by volume, so you can find out the density. So this is the rubber balloon method. And this is a nuclear gauge. So obviously there is a photon source, and then it's very easy. Just go to the site, and there is a smooth surface, and then compact the this rod with this rod, and make a hole into the ground, and then just place that on the top, the instrument on the top of that, and then it will immediately give you how much is the weight density. And then also this is the one in place if it is a rock filled soil. So then you need to use like a water replacement test. So we need to put a polythene over here, you can see, and then use the water, and then density of water is known, so you can easily find out how much is the density. So these are all like a field density method. So basically what you need to do, from the lab test, you know the laboratory density and optimum moisture content. And then you go to the site using different type of compactor and stabilizer, different type of roller and compactor. And then you just take out the soil sample and check how much is the relative compaction. So, and then find out if it is relative compaction is 90 to 95%, then you are good. So basically the lab test is a control test. You will get all the time, you will get the maximum density. Same soil if you're in the field, because here is huge area, we have roller and compactor, using, this is not very controlled test. So basically, if you get 90 to 95% of that, the lab density, then you are good. So what is the relative compaction? Relative compaction, how much is the density at the field divided by how much is the maximum lab density times 100%, you will get that. So in the compaction system, in civil engineering practice, what you do, design problems. So we are doing earth dam, highway, railway road, and levees in the structural field, design engineering properties, so engineering properties, strain, compressibility, all this stuff, laboratory test, and then you do specify design values, how much the relative compaction is required. So you need to do that. And the compaction specifications, compaction control test you need to do. And then finally, the quality control. So if you go to the site and say, okay, this is 90-95% of the lab, then you are good. So again, just for example, over here, 3 hypothetical field compaction tests in the same soil, but different compacting effort. Okay. So over here is the dry density in y-axis, and this is standard Proctor test, right? Proctor compaction test and water content. So there are, you see the different. This is hypothetical test, and then but different, same soil but different compacting effort. So you see that graph 1, obviously you put more energy, that's why the density is increased, like a modified Proctor. This is number 2. Number 3 is a less effort, and then this is the line of optimum. So this is the line of optimum moisture content. So optimum density, you just put the line of optimum. This is the 100% saturation line. So here, so from here, what is the most water content you need to use? Okay. So just for example, if you see that the maximum density is achieved is for this graph 1, right? Maximum density is achieved graph 1. And this is the line for 90% relative compaction. Relative compaction is 90%. So now, what do you think we should use that water content to at the site? Anyone can tell me what should be the good range of water moisture content you need to use? Can anyone tell me the range of moisture content you need to use at the site? This is the lab test. One. Can you hear me? So here you see, what you see over here, the water content is number 1 is A. So this is the moisture content is A, and this is number C is at the x-axis is C, correct? So that is the range of water, we can use A to C, but in the field, if you see this C is basically, C point is, if you consider the first graphs, that is the wet side of the optimum. The soil will be much wet. So ideally, you can see here, the same as the same soil, optimum moisture content for C is here at this is point B, correct? So ideally, you should use close to basically from the moisture content from A to B range. If this is the moisture content, that is much better. So, or you can use the optimum moisture content for 1 over here, 1 from here to this point B. What is the water content? So this will be the good range of water you can use at the field to get that the maximum density. Okay. So variable is the vibratory compactions. Again, densification of the soil, compaction of the compactor, we need to check. Characteristics of the soils, we need to check. Initial density, grain size, and water content. Construction procedures also we need to check. So a lot of things we need to check during that at the site of the vibratory compaction. I'm not going to go in detail over here. So idea is, so laboratory tests are conducted to basically how much is the maximum density and water content is required for that particular soil, and go to the site and add that much quantity of water or moisture so that you'll get the maximum density. That's the purpose, right? End product specification. So we need to check specification used to mostly for the highway and building and foundations. So basically, you check the if the ready compaction is 95% of the lab, then you are good. Care the results only. Again, method specification is typically used as large compaction project. So basically, what you need to do, type and whatever the roller, number of roller pass, as well as the lift thickness and the specified maximum allowable size of the material may also be specified. So this is again, this is method of specification. And the relative compaction, as I mentioned, there are you can find out how much is the density, dry density at the field divided by how much is the maximum dry density at the lab times 100. You know, you can easily calculate. There are a lot of correlations that are available. Relative compaction with the relative density over here. You know, the relative density is E max minus E divided by E max minus E mean. So how much is the maximum void ratio and minimum void ratio? If you need to know, then you can find out that relative compactions. And typically, as I mentioned, that 90 to 95% relative compaction. Then, so basically, that up to that portion is the basically shallow compactions. And I mentioned shallow compaction can be achieved using different type of roller compaction. And the load is basically, it can be static, it can be vibration, it can be leading action, or it can be combined, or it can be mostly, so all these different type of load. Now, blasting or control explosions. So blasting or control explosion or blast dissipation is detonating a small explosive charge using a dynamite at certain depth so that the ground surface is saturated. It can be saturated or loose or cohesionless soil, such as, you know, that densification of the soil takes place. Okay? So grain size is suitable for the blasting. It's the same as compaction for vibroprodations. Okay. We will talk more about that. Lateral spacing of the charge varies from, so at what depth, lateral distance you need to put that. So varies from 3 meter to 9 meter, the lateral charge. And usually explosive charge are placed at a depth of 2/3 of the thickness of the soil layer required to be compacted. So this is very important. 2/3 layer of the thickness of the soil layer required to be compacted. So we need to put that explosive and that at that level. 3 to 5 successful detonation.
उसके भी यहाँ पे हुआ नहीं अभी तो टाका आज कटा हुआ ठीक है ना अभी तो ही चल रहा हो हाँ चल रहा है.
So usually 3 to 5 successful detonation are usually necessary to achieve the desired compaction, and also the compactive effort up to relative density of 80% up to depth of 18 meter or 60 feet over a large area can be achieved using this blasting. Okay. So while doing this blasting, obviously you need to check that explosive charge are buried at a depth and detonated at precise timing to achieve the soil compaction. So while doing that, you need to use the multiple charge or detonation at close time frame. So you need to have few, you know, at certain spacing, you have few charges, and it causes, if it is saturated soil, it causes liquefaction of the soil. So you can see that charges point, the water will come out because the pore pressure releases, and followed by dissipation of the pore pressure and leads to consolidation over several hours. So again, consolidation takes place. Advantage of controlled explosive compaction is can reach far down 50 meters. So it's really quite a depth. And also we'll talk more about that, dynamic compaction. So, but this is blasting. So what happens over here, if you do the blasting, breaks down soil structures, reorientation of the soil takes place, and volumetric reduction of the soil up to 10%. So these are the things happen. So now, how much? So if you put the blasting, control blasting, how much the area of influence will be? That depends. The sphere of influence using by this equation, you can find out the Mitchell's equation, 1970. WEX, that is the weight of the explosive used, and then C is the constant you can use for, and then you can find out how much the radius of influence. Because if you know the area of influence, you can find out how much at what the spacing you need to use this for the blasting. So these graphs will give you a guideline, like how much. So this is the Mitchell test, uses 2.5 kg of charges of galamite number one. So again, you see here M1 and M2, these are the different locations. And then test different tests they did. And then you see for test 3 and 4, more tests is more settlement, obviously. And then in Netherlands, you use like a charge of 10 kg of TNT that's tried not to toluene, and each depth of 15-meter depth default and surface space of 15-meter apart. So if you do that, the spacing, and then you can get that that how much the maximum settlement you require. You need it. Now, so I have just one question now over here. Now I'm going to talk about the deep compactions. So I want to ask like for the compaction, field compaction, you use the different method you use. Like one is the core cutter method. So you go to the site, use a mold and push it into the ground using a dolly and hammer, and then take out all the soil. Mold plus soil, you just find out, take the weight of the mold plus soil, remove that weight of the mold, you know the weight of the soil, you know the volume, you can find out the density. Same thing you use for sand replacement, you can find out how much is the field density. If you use rubber balloon method, you can use that. If you use nuclear gauge, you can use that. So do you think that, so every method, ideally, it should give you, whatever method you use, ideally, you should get the same density, correct? What do you think? It should be you should get the same density, correct?
Ideally, yes.
Ideally, yes. That's good. But the thing is, if you use different method, like if you use rubber balloon method, just for example, if you use sand replacement, do you know that which one is giving higher value? Will give higher value?
Core cutters.
No, I'm just telling just rubber balloon and sand replacement. So what do you think?
Sand replacement will give higher value, my guess.
No. So, I had experience, that in Paradeep, that now Indian oil refinery is there now. So we used to do a lot of tests, that sand replacement, our client was EIL, and then we used to do a lot of tests. So most of the time, this rubber balloon gives higher value compared to the sand replacement. So we used to do EIL, we used to do the sand replacement, and then both tested we used to do, and then also we used to do the CPD test, the cone penetration testing later on, and then we check the density. So again, this is depending on your need. You can use it. What method do you need to know? But mostly the core cutter is the easiest way, and you can find the actual one. But my experience, I'm just telling you, like a rubber balloon gives higher density than sand replacement method. But obviously here in the US, most of the time people they don't do this. Just nuclear gauge. It's easy and quick. So now I'm going to talk about this dynamic compaction or deep dynamic compaction. So it depends. So it's very, very simple test. So shallow compaction, we mentioned that there are different type of roller, and we mentioned there is a limitation. It can go up to a certain depth. So when you need higher depth, so when you have to do either a dynamic compaction or deep dynamic compaction. So deep dynamic compaction is first used in Germany in 1930s. So it's a very simple method. So which heavy weight known as pounder, just suspended from a crane and just drop it. Okay, it's very simple. And then how much the depth of densification is going to occur, it depends on, is in meter. There's the equation, D is the depth of densification approximately square half 0.5 times square root of WH times H. So where WH is the height of the dropping weight, okay, and then H is the height of drop in meters. So if you do that, you can easily calculate how much is the depth of densification. I put some of the YouTube link. Anyone can check. It's very simple. here, the impact, so basically what happened is we just drop the weight. So impact produces the shock waves that causes densification of the unsaturated granular soil. So again, the surface wave, Rayleigh waves, so all these things is going to occur. And then if a saturated soil, granular soil, the shock waves can produce, obviously, and then it's partially liquefaction of the sand may occur, and the conditions similar to quicksand and followed by consolidation and rapid densification. So this is happening when you impact the soil. So how that the shock wave basically propagates and densify the soil. The equation is the same again. How much is the, you need to know how much is the depth of improvement. So D is equal to N times square root of WH. WH over here, the weight of the pounder and the height of the fall. There is a table for N. It's at different factors. So you can easily calculate so what type of soil, how much will be the depth of densification. And you can vary so many things. You can increase the height of the fall. You can increase the weight of the fall, all these things. And easily you can calculate how much is the depth of densification you need. So this is important parameters you need to know. So basically you need to, there is a huge crane is required to lift 10 to 40 tons of the pounder to height around 25 to 100 feet, and then drop this weight onto the ground. Okay. So cost-effective method to densify loose sand and silty soil up to 15 to 30 feet deep. So 15 to 30 feet deep if you want to improve the strength of the sand. So this is a good method. So you just drop it. So degree of compaction again depends on the weight of the hammer, height of the hammer drop, and the spacing and location. So what is to be the spacing? So there are different things we need to check. There are primary impact, there are secondary impacts, all these things. And the deep craters are formed by tamping. So and then later on, this crater, when the compaction is done, then later on, this crater will be filled with sand after every passes. Okay. Suitability, again, the loose and partially saturated field, saturated free draining soil, silt and plasticity index less than silt with plasticity less than 8. This is good. Clay soil with low degree of saturation, and then also generally not recommended for clay soil with high plasticity index greater than 8. So it's not suitable for clay. Reduced effective means the water table is within 2 meters of the starting level. So the water level should be below. So that is good. And this is economic for sites more than 5,000 meters square, and a certain clearance is needed, because if you are doing this impact close to a house or anything, then that may create a detrimental effect to the existing or nearby building. So this is in Shanghai, that the deep compaction is a huge site. They are using this. So as I mentioned, the N value over here, D is equal to a depth of improvement or depth of densification is equal to N times square root of W times H, where N is the coefficient that accounts for soil type of pounder, falling mode, so all these things. So again, different people have given different N value for different type of soil. So we need to check that. This will give you a guideline to select what type of, how much the depth of improvement they need. And then you can use these values, N value, to calculate how much is the depth of improvement. So N, the variation of N attributed to the efficiency of the drop-off mechanism of the crane. Total number of energy applied is 0. So type of deposit being densified, so presence of energy absorbing layer. So a lot of things you need to check. Contact pressure of the tamper. So all these things you need to check. Okay. Then phasing of dynamics. So obviously here you can see here, this is, so the dark one over here, this is the main first phase, compaction of the deep layer. The first layer is the dark one, dark yellow color. And then first you do all the dark one. And then you go in between over here. This is the second phase, a compaction of intermediate layers. So do this compaction, the second phase. And then obviously you are ignoring this phase, right? The square one is not everywhere. So you need to see for one influence, one impact, so how much is the area of influence? So we need to check that, and then and that is good enough for the improvement. So over here, the property changes with depth. Obviously, as I mentioned, so it is going like a so like as a cone type of stuff. So when you apply load in a soil stress, like a 2:1 or 1:1, like a load distributions, it's load like that. So it's ignoring phase one. There's the first phase, and second phase is the second one, over here, and how the density is increased with these impacts. And again, there's a square pattern or triangular pattern are commonly used depending on how you're going to do that. So again, as you have seen, over here, this is a square pattern. This is a square pattern, so it can be triangular pattern also. All right. The crater depth. So when you impact, it causing a crater. So high energy applied can result in a crater of 1.2 to 1.5 meter deep. Crater depth should be limited to height about tamper plus 0.3 meter. The depth of loosened upper zone about crater depth again, and then the loosened soil zone should be densified by ignoring pass. Okay, so a few things need to be checked, and this is how it looks like after dynamic compaction. As I mentioned, it should be filled with. This is the hammer. It should be filled with sand later on, and place your actual structures. So what is going to happen when you impact it? So how much is the peak particle velocity? We need to check. So we need to calculate the peak particle velocity. High energy impact on the ground reduces environmental impact, mostly vibration, noise, and lateral ground movement. So basically, how much the Rayleigh waves, different waves. So upper limit of peak particle velocity, Main et al. 1984. So peak particle 70 times square root of WT HD by XDP, power 1/4, power 1.4. So this is stamping weight, drop height, drop height, and the distance from the drop point. So you need to calculate all these stuff. So find out, sometimes the peak particle velocity is very important. So, you have an idea. So we have, so different thing for different soils, peak particle velocity and the energy you can find out. So it is sometimes this peak particle velocity is very disturbing. It's not disturbing, strongly perceivable, and the slightly perceivable. So depending on the situations over here, so how the typical particle velocity is 20 to 40 millimeter per second. It is good for a structural or commercial building. The threshold velocity, it should not be more than that. Residential construction, it should be 5 to 15. And for sensitive, it should not be 3 to 5 millimeter per second. So impact, we cannot just dynamic compaction can be used in that area. So now the thing is, sometimes if you have a building over here, you are using a tamping. So sometimes you have to do the cut-off wall, so that the velocity will not travel. You need to cut a trench so that it will not, the wave will not move, okay, to the building. So this is good. Sometimes, so this generally we generally use this when you are designing a machine foundation, right? So foundation, so we need to do a cut of trench so that the vibration will more. So we call it the vibration isolation, right? The same things, you can do that. If you want to use this dynamic compaction, and there is a building nearby, so you need to use this cut of trench, okay? So this will give you an idea, suggest the range of treatment depth varies with initial strength and soil type and energy input. So you can easily find out from here if it is a loose or weak soil. So, and then how much energy you need to put. And then again, everything is related, right? So how much the D is the depth of densification, how much is the weight of hammer, and how much is height of foam. So all these things are related. So this will give you an idea. And then, so how much the energy you need, how much the depth densification you need. So if it is a weak soil and if it is a steep soil. So if it's a weaker soil, you see, you need more impact, or, you need more energy. So there are many factors affecting the dimensions. So again, the type and competition, the competence of the surface layer, position of the water table is important, number of drop at each location is important. And the knowledge of depth at any stresses impulses is a vital factor, so it's very important. And also kinematic energy. So most of the time, there are different criteria. In the Britain, just for example, velocity is 30 mile per hour is a mini scale method. Effective depth of treatment 4 to 6 meters. Velocity 50 mile per hour full scale method. So, and then this is treatment method is 6 to 8. So these are the few things you need to check. And so dynamic compaction, few things you need to check over here. I just want to mention that generate a surface wave. So obviously when you impact, because of impact is a surface wave, dominant frequency of 3 to 12 hertz, and vibration generates 3 types of waves: compression, shear, and Rayleigh wave. Rayleigh wave contains about 67% of total vibration energy. So this is very important, the Rayleigh wave, and becomes predominant over other waves. Other wave types comparatively small distance of the source. So the Rayleigh wave is important. And the Rayleigh waves are the largest practical interest for the design engineers because the building foundation are placed near the ground surface. So the top surface, Rayleigh wave is important. And there, so peak vertical velocity is very important there. So peak vertical velocity is the maximum velocity recorded at any 3 coordinates axis. So we'll see the figures, and then the measurement of the vibration is necessary to determine the risk of any nearby structure. So you need to know that. So this will give you a guideline, all these graphs. And vibration can estimate through empirical correlations measured with the help of instrument, like a portable seismograph or accelerometer, or velocity transducer, or simple LVDT. Okay, so this will give you a guideline, like a peak particle velocity and the scale distance. And the frequency of the Rayleigh waves decreases with the increasing distance from the point of impact. So as you go far distance, this impact is less. And the relationship between the peak particle velocity and inverse scale distance is shown graphically over here. You see the scale distance and the peak particle velocity. So this will give, you can adjust everything depending on the instrument. So you have huge cranes. Sometimes you don't have huge crane is available. So what you need to do, so height of fall will be less, correct, in that situation. So you can use the weight of the hammer itself, okay? And then you can do, it will be the same thing. So how much is the energy, like a kinetic energy, right? So WmgH, the simple thing. So, and then the peak particle velocity, you need to check how much the velocity travel. And then depending on that, whether it is detrimental to the adjoining structures, that also that will give you a guideline. So I'm not going to go in detail. So over here you can read that. So you see the upper vibration limit of the vibrating operator is frequency 30, and the lower is 50 hertz. So this is the limit generally used. And in addition, the magnitude of vibration, typically frequency range of 5 to 15 is potentially 5 to 15 lower frequency is potentially damaging the structure, and that is particularly noticeable to human beings. So basically, if the lower frequency is not good. So this will also give you some guide. Here is the same thing again, the structural damage. Earlier I mentioned 50 millimeter per second. Minor architecture damage is the velocity, peak particle velocity is 10 millimeter per second. Annoyance to occupants is like the existing building is 2.5 millimeter per second. So again, 3 main things. Vibration becomes a problem when the 3 main methods to reduce their effect. The first thing is to simply reduce the height of the drop. So depending on the situation, and compensate by increasing the number of drops. So you just reduce the height of drop. But number of drop is more. Same thing like a standard proctor and a modified proctor. So the modified proctor, the weight is increased, and then also the number of layer is increased, right? So number of drop is all the same, 25. So these reduces both impact energy and the penetration of the stress impulse that may attain an unaligned or a dense stratum. Second method, reduction of utilizing smaller weight. You can reduce the small weight. And the third, to excavate a cut-off trench, as I mentioned, so that you just cut off the velocity is traveling, right? If the horizontal travel to the ground. So obviously, if you cut off trench, that will basically isolate the vibration. Okay. So now, there are special deep compaction techniques. So we have fiber compaction method, we have fiber replacement method, you have fiber composer method, and then also cased boron method. So there are several methods. So first thing is we talked about like a normal compaction, normal different type of roller compactors. There is a limited depth. And then we talked about dynamic compaction. So dynamic compaction, because of dynamic effect, can go higher depths. And also you mentioned that control blasting. Okay? So now the special compaction, the fiber compaction method, fiber replacement, and fiber composer, and then also cased borehole method. So here, first one is the fiber compactions. So fiber compaction method is the fiber compaction method is used to densify the cohesionless soils or granular type soil using a fiber float. So this is a fiber float. So we'll see some more picture. So basically, what is happening? You need to make a borehole, and then using a fiber float, insert it into the soil, and then put gravel from the top, and then you can compact that gravel. So the fiber compaction is suitable for granular soil. So this is if you construct like a stone column, you can use this the exact same method. Fiber compaction is suitable for granular soil with silt content up to 10 to 15%. So this is really suitable for gravel type of material. The presence of fine in exceed of 20% may, so if the fine content is more than 20%, it's not good. It's not an effective method to use this fiber compaction. So again, as I mentioned earlier, the vibration is good for granular type of soil, sandy type soil. Same thing also. The vibro, so obviously is suitable for granular type of soil. So SPT value of 5 to 10 near surface is not applicable for clay. So when SPT values on the surface is low, it's not applicable. Again, it's not applicable for clay. Fiber compaction can be used to compact granular soil up to a depth of 40 meters. So it can use up to 40-meter depth. And using a fiber float, which sinks the ground under own weight, 4 to 8 ton weight, and length is 2 to 2.4 meter, 2 to 4.5 meter, made with assistance in water and vibration. So there are this fiber float, there is a water jet attached to this. So most of the time when it's go inside, it's the water jet, and then it's making a hole, it's go down. And then the gravel is added to the top, from the top, and then it just vibrates, the ground, basically. So fiber compaction method. So compaction is selected location using a vibration and vibratory equipment, resulting in compaction at larger depth. So you can go up to 40 meters. Zonal compaction around a single float is a function of type of float. So again, what type of float you are using. And the success of in-situ densification depending on the grain size division of the in-situ soil and the backfill soil. So this is important for the what type of soil they are at the particular site. The use of grown size analysis of soil to decide on compactability. Again, obviously the compaction is depends on the well-graded or poorly graded. All these things you need to check. So base suited for, obviously, as I mentioned, so it is suitable for cohesionless, clean cohesionless soil with certain percentage, limited percentage of fines allowed. As you mentioned, that ineffective when the fine particles percentage passing is less than 200 millimeter sieves or 0.075 millimeter, not 0.74, it should be 0.75, is more than 25%. So, and then ineffective if the situation due to the decreased impermeability of the material is excessive fine. So again, that is also not good. So, and then as I mentioned, using a fiber float, it gives the horizontal motions from the vibrator inserted into the ground. Okay, so I'm just going to show you some pictures. Applicable soil, I'm going to go in detail. So this is fiber flotations. This is the particle size range. So basically, you see here the gravel. The most desirable soil range is gravel to sand. That is very good to use this fiber flotation technique. I'm going to go. So this is fiber flotation techniques over what you need to do. So basically, it's a technique in-situ densification, thick layer of loose granular soil. And again, also it's developed in Germany. So what you need to do in a fiber float or vibrations, so 3-element extension tubes and the crane and jet water supply and pumping. And so basically, in front there's a jet water supply, so it can go down and then it can vibrate. So over here, so obviously, so first you make a hole into the ground, and then it can vibrate, and then add from the top like a gravel material, and then it vibrate horizontally. So and then it can forming a column, basically, sand column or gravel column, okay, or stone column, you can say. This is very common. This is the picture I took it over here. So if it is a clay type of soil, this is sand column, but that stone column construction site. This is when the soil is good, clay type of soil, using this boring method. Take out the soil sample and check it so that the sample will go, and then after we make a hole, just cover it. So this is the spacing between the center to center of this different stone column, and then using this vibrator, at every steps, and put a gravel. Most of the cases in the US, we use that CS6 gravel material for this stone column or vibro compaction technique. And then how it looks like. So this is the vibro float. So it really vibrates. And at the point over here, there is holes and the water nodule, so it can really vibrate, and then compact the gravel. Okay. So vibro flotation method. So what you need to do, first thing is a stage one is a jet of bottom of the vibro float turns in the lower into the ground. So obviously there's a water jet, so that will create a hole. And then water jet creates a quick condition of the soil, allows the vibrating unit to sink to the ground. So the vibrating unit sink to the ground. And then what you need to do, add a gravel material from the top, and then it vibrates. So basically, it was up to here in third step. And then you just compact this, and then from the lower part, and then lift it up. So after compaction is done, you just lift it up, and then you're forming the solid column, okay, on soft clay. These are the different vibrating units. So I'm not going to go in detail. So different 100 horsepower electric unit, 30 horsepower electric unit. What should be the vibrating tip? Eccentric load. So basically, because of eccentric load, it vibrates. And then what type of pump you use. So all these things. This is from the Brown 77. And then also we have the lower follow-up pipe and extension. So obviously you can use different type of diameter and weight. So how you're, again, nature of probe spacing. So it depends on, and the blue color is the probe spacing where you're putting that probe, and then you can do it. So basically this is like a triangular type of arrangement. If you see blue dotted line, if we add this, so this is basically the triangular, and then the sample is compacted over here in the whole area. So, for stone column, generally you need to know later on the how to area replacement ratio and other things. But here you need to do much over here. Then vibro compaction now is a vibro replacement. Okay, so vibro replacement method is used to improve the strength of the cohesive soil when. Basically, it's for clay type of soil. So we need to do. So what we need to do to achieve this, you use the vibrating probe similar to the technique. It's a vibro compaction, but the probe is allowed to penetrate the soil and does so by displacing the soil radically. So that's how you do. So it can be either wet method or dry method. So both methods can be used. And when you use this soil, when the undrained stem, the soil is more than 40 kilonewton per meter cube. So that is. So obviously, what you need to do is a clay type of soil, cohesive soil. So when you make a hole, it should not collapse, correct? So and the strength of the clay is at least it should be the compressive strength cohesive strength should be at least 40 kilonewton per meter square, so that it can stand at its own. Okay. So vibro replacement again. So this is replacing. So what you need to do, you take out the clay and then replace it. Okay. The stone columns extend the range of soil that can be improved by vibrating technique, including cohesive soil. And then also the cohesive soil is basically you are densifying the soil on the side. So basically the consolidation takes place or compaction takes place. Densification or reinforcement of the soil as a compacted granular column, stone columns, is accomplished by either top feeding or bottom feeding. Again, I'm not going to discuss this top feeding and bottom feeding method. I think Dr. Strelija, maybe Dr. Bawal is going to explain this method. And then the cohesive soil mixture, the soil generally do not densify easily when subject to vibration alone. So again, so that is the difference between this replacement and also that vibration. So over here, it's a vibro compaction. Why we use and vibro replacement? So obviously, vibro compaction is good for sandy type soil or gravel type of soil is excellent. And fiber replacement, this is not suitable. For sandy type soil, silty sand less than 20% fines. So again, I'm talking about fine means particle size is less than 75 micron or whatever the passing number 200 C, meaning it's less than 0.075 millimeter. And then this is good fiber compaction. This is good for fiber replacement. For silt, it is fiber compaction is poor. Fiber replacement is good. Clay is not applicable. You cannot apply because no vibration. So fiber replacement is good. So these are the different things. Which method is suitable for fiber compaction or fiber replacement? So, and then fiber composer methods. So this is a popular method in Japan, used for stabilizing soft clay in presence of high groundwater level. So you can use that, resulting the piles usually known as sand compaction piles. So most of the cases it's the sand compaction piles, or here in US, most of the time we call it the drill pyre or pyre, and then a heavy of 0.4 to 1.5 meter diameter casing is required to driven down the required depth, and by a vibratory hammer located at the top of the casing. So sometimes, again, if you're using sand, so obviously if you're in clay, so obviously what is going to happen, then you need to use a sand geosynthetic casing so that it will not mix with sand and clay or sand and gravel. And the spacing is normally between 1.77 to 2.5 meter. So this is the particle size range for fiber compaction and fiber replacement. So mostly the fiber compaction is the sand and gravel type. You see the range over here. And the fiber replacement is replacing. So you can do mostly for the clay, so you can replace any type of clay and then or gravel, and then you can either using top feeding or bottom feeding method, and you compact it. Only thing is depending on how much is the stiffness of the clay. If it is too soft, so then there is no lateral confinement. The problem is if there will be settlement, and then also there will be bulging of takes place of the steel. So these days that's why people are using geosynthetic enclosed stone column or geogrid encased stone column for this fiber replacement method. Okay. So when using fiber compaction, it is necessary to supply additional material to achieve the required densities. To fill should be sufficient enough to transmit the vibratory action to the surrounding in situ material. Coarse granular material with little or no fines provide the best materials and allow faster rate of compactions. And also the Brown also developed a rating system for the imported fill material. So again, sometimes we need to have the granular fill to fill the hole, correct? So sometimes you need to transport that gravel type of material from a far distance. So sometimes if you find some locally available materials, so these days people are using even recycled material into that as a fill material. And then also the Brown's system, he developed a number called the stability number. So it is shown in here. Suitability number, how much? So again, is the equation is 1.7 square root of 3 by d50 whole square plus d20 whole square divided by 1 plus d10 whole square. So obviously, d50, d10, d20 from the particle size distribution graph, you can find out like a 50% finer, how much is the percentage, the particle size, 20% percentage finer particle size. So 20% come down the how much is the particle size. Millimeter, so you can find out that, and d10. And if you know this d50, d20, and d10, use this equation, find out how much is the stability number. So if it is a lower number, is good. So if you get 1 to 10, this is external material, gravel materials, gravel type of materials. If you get like a 10 to 20, is good. If you get like the higher value is not very good. So that's the thing. For the backfill material evaluations according to the Brown stability number. All right, I think that's all for this up to this the different compaction techniques I just explained. So I have gone really quick, so I don't know how much time we have. So we have Dr. Senthil or Chure, can you just tell me how much time you have now?
Yes, sir. Time is almost completed, sir.
Oh, okay. Yeah. So I have just gone very quickly because the syllabus have given to me, the syllabus given to me is really, there's so many material. I have to go. Otherwise, I have just gone right so fast. So otherwise, I cannot finish it. So I just, if you need, because there are a lot of things we need to know and we need to go more detailed. And then maybe we'll solve some problem maybe tomorrow. Some assignment problem or some tutorial problems I'll be solving. So anyone has any questions? I don't know. I mean, there are so many topics we
Sir, I
explained.
have one query. In the
Yeah.
deep dynamic compaction that you mentioned, like it seems to be very much like in nearby structures, it will impact significantly. So,
Yeah.
like one of the trenches method that you explained, but how much distance we should think about wherever it is being applied, deep dynamic compaction, sir.
Okay, so that's one again. I can go much more detail. I mean, that one, most of the cases when you design like a machine foundation, just for example, right? So we need to do the vibration isolation, right? So it depends on. I can solve some problem maybe, or I can send some material to you so that it will be much easier. With the I cannot tell exactly at this point on the top of my head, but I can send some material so that you can. So basically here, whatever we explain is just guidelines. All these peak particle velocity and other things and the energy you can readjust the weight, hammer, height of drop, all these things, and then so this will give you a height guideline and also what type of frequency you are using. So that will tell you, and then which one is detrimental effect. So so you need to check all these factors, and then you need to see, which one is best suited for a particular site condition.
Thank you so much, sir.
Yeah, I can send some material to you, so that you have an idea.
Sure, sir. It will be really helpful.
Yeah.
Thank you, sir.
Yeah, I mean, here in these classes, I mean, this course is very basic. I just talk about the compaction things, the very basic, that simple thing to, again, different type of roller compactors. Everyone knows, but again, how much is the depth and the deep dynamic compaction, and then also that vibro compaction and vibro float. I mean, we can take vibro float and vibro compactions 2 days, but because of limited time, we really cannot do much. Any questions? I know it's very quick and it is just like a one-way teaching or explaining something. It is difficult. Several topics and then also less time.
So, sir, I think there is no more questions.
Okay. All right. Thank you so much, everyone, for listening to me. All right.
Thank you, sir. Thank you so much.
Yes, sir.